If you look closely at the very first aircraft, you'll notice something missing. They didn't have wheel brakes. These early planes landed at slow speeds on soft, grassy fields, so to stop, the pilot relied on dragging a heavy wooden stick, a tail skid, straight through the dirt to create resistance. As planes moved from grass to paved runways, they began landing much faster. To stop that much weight moving at those speeds, you have to find a way to trade that motion for something else. When two surfaces rub together, motion converts into intense heat. This is how modern aircraft brakes work. A stationary clamp squeezes a spinning metal disc on the wheel. The harder the squeeze, the more the wheel slows down, and the hotter the metal becomes. If you are curious about the engineering behind how things fly, hit the subscribe button. We break down complex aviation topics every week so they're easy to follow. Stopping a plane isn't just about applying pressure. It's about creating a system that can soak up that massive burst of thermal energy without melting. Small training planes use a single disc setup on each wheel, which is a lot like the brakes you'd find on a typical car. On the floor of the cockpit, the pilot has two pedals used for steering the plane on the ground. To stop, the pilot presses the top of the rudder pedals, pushing a piston inside a hydraulic chamber. That fluid travels down a line to the wheel, providing the muscle to pinch the disc. Pushing harder builds more pressure, squeezing the brakes tighter. Because this system is separate from the rest of the plane's mechanics, the total stopping power is limited by the strength of the pilot's legs. This works for a small plane, but it's not enough for a massive jet. Commercial airliners weigh hundreds of thousands of pounds. No human is strong enough to stop that much weight with their legs alone. These large jets use power brakes, which use the plane's high-pressure engine systems to provide the heavy-duty squeezing force needed to stop. Stopping a jet also creates way more heat than a single disc can handle. To manage it, engineers use a stack of several discs that all rub against each other at once. This creates much more surface area to distribute the heat, so it doesn't build up in just one spot. Even with multiple discs, standard metals can still warp or melt under these conditions. This is why many modern jets now use carbon fiber discs. They can survive temperatures that would destroy steel, stopping the plane safely flight after flight. As planes get bigger, the engineering focus changes. It's no longer just about the physical squeeze. It's about finding materials that can survive the incredible heat that stopping creates. Because the hydraulic pressure on a large jet is so high, it's very easy for the brakes to lock the wheels completely. If a tire stops spinning while the plane is still moving, it will skid across the runway and blow out in seconds. To prevent this, planes use an automated anti-skid system. Small sensors on the wheels watch how fast each tire is spinning and report back to a central computer. If a sensor sees a wheel suddenly slowing down too fast, the system knows a skid is about to happen. An automatic valve briefly lets some of that fluid escape, easing the squeeze just enough to let the tire spin again. There's also a physical safety lock preventing brakes from working in the air. A sensor on the landing gear strut detects when the plane's weight is on the wheels. Until compressed, the system stays locked out. Human reflexes aren't fast enough to modulate pressure this quickly during a high-speed landing. These automated systems are what allow such heavy machines to stop smoothly and keep their tires intact. Because of the extreme conditions these parts face, mechanics have to inspect them constantly. They check the thickness of the brake pads, much like you'd check the brake pads on your car, to make sure there's enough material left for the next landing. They also look for dragging, where the brakes don't fully let go after the pilot releases the pedal. This often happens if tiny air bubbles get into the fluid. When those bubbles get hot, they expand and start pushing the pads against the disc when they shouldn't be. If a pilot reports loud squealing or vibrating, it's a sign of heat damage. Intense heat causes flat metal discs to warp and become wavy. As they spin, they rattle against pads, creating noise and shaking the landing gear. These sounds and feelings aren't just annoyances. They are the physical evidence that the hardware is being pushed to its thermal limits and needs professional attention. The most extreme test for this system is an aborted takeoff. If a fully loaded jet has to stop suddenly while it's already at high speed, the brakes absorb all that energy in just a few thousand feet. It's common to see smoke and heat waves pouring off the wheels afterward. After an event like that, the brakes are usually finished. Mechanics have to take the whole assembly apart to check for melted seals or cracks in the metal caused by the sudden spike in temperature. In these emergencies, the brakes are essentially designed to be destroyed. They are the final line of defense, designed to soak up enough heat to keep the rest of the plane and the passengers safe, even if it means the brakes themselves never work again. From dragging a stick in the dirt to using computer-controlled carbon discs, the goal has always been the same: finding a safe way to turn speed into heat. It's a simple rule of physics that keeps aviation moving and stopping safely.